So in this chapter we're gonna be doing the splitting of our mesh in order to create the blinking attributes, as I call them. We are going to start with the creation of an attribute called IDS with an attribute triangle. I usually create attributes, like usually some people, they create, some artists, they attribute create like this. They do an attribute create. This allows them to set a default and initial value, but I know that my entire mesh is going to have this attribute, so there's some scenarios that attribute create works best, just to be on the safe side, but I'm going to use the attribute triangle. I usually create attributes like this. So why am I creating this IDS attribute and not an ID attribute? Because Vellum has internally, it already uses an ID attribute, and if you try to connect a geometry that has an ID attribute already into the Vellum solver, it's going to give you an error saying that you have a duplicate ID attribute. So in order to avoid this, we'll be doing an IDS attribute. That's what I use for these kind of scenarios. Why am I doing this? It's because we're going to be copying attributes from body parts to body parts, and I'm going to split the mesh into several pieces, and we'll need this attribute in order to match vertices when we attribute copy. So yeah, we're going to be splitting our mesh into separate groups that will be animated separately by different Vellum nodes. So I'm going to blast, first I'm going to blast the legs, delete non-selected. So we're going to be creating blinking attributes on the legs, and you'll see how we do it. And you'll see why I've made so many groups. We already have a class attribute here, but I prefer to recreate it now. Because we have 3 legs, I want to have a class attribute that starts with 0 and ends with 2, because we have 3 legs, so it's going to be 0, 1, 2. We're going to recalculate the connectivity. Have this primitive class attribute. I usually create the primitive class attribute, and then I can promote it, or you can already create the connectivity as a point attribute. I sometimes prefer to go back if I need to and remove the attribute promote, leave it as a primitive attribute. So we're gonna do it as I did it before, primitive point class attribute. So if you open the spreadsheet, I only open the spreadsheet when I have issues that I need to solve and I have to debug the entire node tree. So I don't like to keep it on the screen all the time, unless I'm only doing debugging. So yeah, so you see we have a class attribute. We can even display it. You see that it displays as color, and we're gonna display it as marker. So leg 0, leg 1, and leg 2. It just randomly chose this order. It doesn't really matter, but because we'll be using this attribute for randomizing seeds and randomizing timing, we're gonna do the same with the bubbles. Duplicate is blast 2 times. We'll be selecting only the bubbles, so you only have the bubbles with their own class attribute, and in the end we're going to be using we're going to be legs. We're going to be removing the legs and the bubbles, and we'll end up with the remaining mesh. So yeah, and here we're going to be just isolating the bubbles like this. So we have the bubbles, we have the remaining mesh, and we have the legs. So now I'm going to create this network box just so we kind of separate what's happening here. I'm going to call it split by groups. Press the C letter on the keyboard, select the network box, make it red so we have some contrast and we see the nodes better. And now we're going to be doing the blinking attributes, which is the core mechanic of this creature, and we're going to be creating it in an attribute triangle. So it's going to include some lines of X. It's not that complicated, but the main expression that we're going to be using is the modulo expression, which allows us to cycle any kind of attribute in time as many times as you want. So I'm going to create a float cycle. First, I'm going to be making a like simple modulo expression, which is the frame that we're on right now, divided by a float channel, which I'm going to call max frames. and this is going to be the cycle. We're going to click here to create the spare parameters, which is the max frames. I'm going to call it 40. And if you visualize this as color, you'll see that. So it kind of blinks, but it goes above what happens here. If you go into the spreadsheet, you see that it goes from 1 to 40 and resets to from 1 to 39 and resets to 0 and restarts the cycle. So 0 to 39. And we need to have a value between 0 and 1. So we're going to divide it again, the whole thing. I'm going to divide it by the same kind of channel, the channel frames. So divided by, and you have an attribute that kind of blinks. We're not using any keyframes. I never used any keyframes on my creatures because I just don't like physical, tangible keyframes in the timeline. I don't want to see them. I don't want to move them in the timeline. It's just, you know, a hassle that I want to avoid. And I prefer to have spare parameters and cycles and expressions and sinus expressions that kind of cycle any attribute in time. And you see, as you see, it just resets to 0 every time we surpass the 40 frames. Our cycle is going to be 40 frames exactly, but I want to randomize this value, the frame. I want to offset the timing of these 3 legs. This is why we had this class attribute calculated and created before. I'm going to be adding some randomization here. I'll add the class of our leg. So you see there's a really slight offset, but I want to multiply this class by another channel, float channel. I'm going to call it f offset. And you have to keep in mind that there's you have to have the correct number of brackets and create the spare parameter that I created, the f offset, and let's say 10, and you'll see that kind of randomizes the legs now, because each leg has a class attribute which is different, and this we multiply this class attribute to this offset, which is 10, and adding it to the existing frame, and each leg has a different time evaluated in this expression. So this is why our cycle is offset in time. So basically we take the time, we randomize it by a number of frames, we divide it, we do the modulo expression with a specific amount of frames, and we divide it back to by the same amount of frames, the whole thing here, which is divided by the max frames, and we're ending up with a normalized value between 0 and 1. This is a cycle that you can do with any kind of attribute. You can cycle attributes like this in time with no issues by using just the modulo expression. So okay, so now I assign this color CD attribute to the entire mesh of the legs, but we're going to separate this. I don't want to do this to the entire mesh, so I do these backslashes. Yeah, and I'm going to be writing some conditions here, just so we separate the parts where we apply this blinking attribute. I'm going to be checking if the in-point group, so we're checking if the vertices in this geometry belong to the group called tips. So the 0 in this expression means the current geometry, the first input in this attribute triangle. So you can see here, this is the first input, which has the index 0, so we put it here. And you either put ptnum or IDS that we created earlier, and we check that it belongs to this group. Then we apply the cycle to the color. But before we apply directly the cycle to the color, I want to pass it through a ramp, which I'm going to remap before it goes into the color. So ch ramp, I'm going to call it just ramp and cycle. So, and we're going to create a CDR attribute, which is going to be an attribute that we use for attaching and detaching our tentacles, legs. I'm going to copy just the same thing here, and I'm going to call trump R, and close this parenthesis. And if you look now, we have a cycle which applies oh yeah, so we didn't apply any ramps here. So for now, we only have the tips blinking, because we checked that our points, they belong to the specific group. And we're going to do the same kind of condition, but for the legs now, because we want to check if the same applies to the legs. And here, we don't want any ramp CDR attributes in the legs themselves. So we're going to remove this and check if the point in this geometry belongs to the group legs, and apply a ramp called ramp A this time. So yeah, we have 3 ramps now. So I'm going to remap them in a different way, all of them, because this is how I've done it before, and you'll see why. I want to remap them properly. So here I'm going to invert this. The first ramp is going to be the CD ramp. This is the ramp that is going to control the force applied to the tips. So I'm going to make a ramp like this, something like 0.21 and 0.2. So yeah, and then the ramp R, which is going to be the ramp that controls the attachment and detachment of the tips from the ground, is going to be similar. So I'm going to copy parameter, paste values, and here I'm going to just make it like 0.06, 0.12, and this is going to be a Bezier. I'm going to make it a Bezier, or maybe not, just a Catmull ROM, I think. Yeah, something like something like this. Yeah. Yeah, something like this. Very smooth ramp that goes into the. Yeah, so 0.12 and 0.06 as position. And for the ramp A, which is the ramp that is applied to the cycle for the legs themselves, this is the ramp that is going to control how the legs are contracted. For the contraction of the legs, I'm going to use tetrahedral fiber constraints. I think this is the most underrated constraint in Vellum, and I really love what it does. It's very similar to the fiber constraints that are in FEM solver. So here I'm gonna put some keys, something like this. So click this button, 0.25, something like 0.55 maybe, and monotone cubic. Use some of these keys too. Yeah. So maybe let's use a B-spline here. Same for this one. So it's a B-spline. It's kind of a mix of a Bezier and a Catmull ROM. Yeah. So this is going to be our ramp now. Yeah, something like this. Yeah. So now you can see that we have the cycles applied to these body parts, and the only thing that I find strange is that the cycles do not appear to be to apply to a separate, because the tips have to be cycling differently. So I forgot to do something in the groups. As you remember, we did the tips. So if you look at the tips, these are the tips, but these are the legs. So the legs contain the tips. This is something I wanted to avoid. So we're going to duplicate this group combine and do the same Boolean operation, subtract from the legs group the tips group. So this is what happens. I just wanted to exclude those tips from the legs. So this is why we had this issue with the with our legs, and then yeah, so now it's removing our legs, our tips from the. So I'm gonna keep the legs and the tips. So yeah, we're gonna legs and the tips. I'm gonna keep them here, do the connectivity, and we'll have this. So these are the blinking attributes that are going to control Joey. As you can see, when the tips are white, the force is applied to the tips. The legs flies up, falls down, attaches. Then you have the contraction of the leg. and then the leg decontracts, and then we have another force applied to the leg. So it's a cycle that allows the leg to be moved in space with a force, and then attached to the ground, detached from the ground, and so on. So we created these ramps just to control the different timing of the legs. It was a process of trial and error, because it needed to be like the timing was a tricky thing for me to find. So it's a trial and error. You do like 50 simulations until you get the good timing. So for now it just looks like flashing parts of the body, but in Vellum you'll see how it translates to movement. We finished here with the legs, which is the main part of the propulsion system. I'm going to make a attribute wrangle for the remainder of the body, and yeah, the funny thing is that I may have done something with the groups. Just a second. So what I also forgot before, when I promoted the group legs and group bubbles, I wanted to keep the original group. Yeah, so we have to go back to the combine and group combine. Same here. There's going to be points for combining the legs with the tips. And then when we do the blast operation, I really want to do the primitives, group legs, keep the legs. Same goes for the remainder of the body. I want to remove everything. And in this attribute wrangle, we're going to be applying creating a CD attribute which is going to be set to 0, 0, 0. So it's going to be black. You'll see why, because we don't want to apply any kind of attributes to this remainder of the body. Yeah, so for the bubbles, we have a class attribute for the entire body, so I'm going to be blasting this, doing you can check delete and use groups. So if you have any groups that are empty, like here you have group tips which is 0, you do the delete and use groups and just removes all the empty groups. Yeah, so I'm gonna attribute promote the class attribute for the bubbles. So it's gonna be a primitive class attribute which goes into a point attribute and it gets promoted, but I want to use the first match as a type of as promotion. So if you leave it at average, it's going to be kind of weird. Some vertices that are shared, it's going to be a tug of war between the class attribute of each bubble, and so each one of them are going to try to claim the shared vertices. I prefer to leave it at first match. And yeah, so here I'm going to copy the attribute wrangle that we did before with the cycles and the whole shenanigans, but I'm going to delete everything except I'm going to leave the same cycle, but I'm going to delete the conditions and leave just this expression here. It's going to be the ramp, the first ramp that we used, and I'm going to try to remove all the ramps that we don't need, except make it linear first, and we're going to just make it like this. Let's say a B-spline, B-spline, B-spline. Make the size bigger, and kind of play around with this. I want this attribute to be turning on and turning off, kind of inflating and deflating. But what we can do here is, because it doesn't go to 0, let's say it's linear, and I make it monotone cubic, so it goes to 1 and it goes down faster to 0. I'm going to use the same cycle, but the offset is going to be 5. So if you look at what happens, so it uses the class attribute to randomize the bubbles. It uses a cycle of 40 frames with an offset of 5. So each bubble offsets its class. It multiplies the class attribute by 5 and adds it to the cycle, which means that every bubble is going to be offset in time separately and differently. Before I was doing this this blinking attribute system in a loop, which wasn't really efficient, and it wasn't fast at all, because basically the loops, the for each loops, are really expensive to calculate when you have big pieces. It splits the geometry physically into pieces and evaluates each piece separately. This is why it takes much more time to evaluate. But using attribute triangles with such expressions on separate specific groups, it's much faster. It's like 100 times faster. Now we're gonna merge these nodes together. So in order to merge these nodes together, we'll line them up like this, select them, alt-click on one of the outputs, and it's going to merge this into a merge node. And now you have all the body parts blinking in their own way, and you see that they all have their CD attributes, CDR attributes. I'm going to also display the CDR attribute. We're going to maybe create also a CDR attribute, which is going to be set to 0 in both of these scenarios, so it doesn't really say anything. So yeah, now we have the blinking attributes with proper ramps. I'm gonna display the CDR attribute. This is gonna be the attribute that releases the attachment constraints from the tips of the monster. And now we're gonna copy these attributes to our original triangular mesh, which is here. And this is where the IDS attribute that I created earlier will come in handy. We're gonna use the attribute copy. This, use the original triangular mesh, and because we have split, like if you do an exploded view, we split the mesh into pieces before. As you can see, it's exploded and the vertices are not welded. So in order to avoid this, the original we're gonna attribute copy the attributes to the original mesh. So we're gonna match by attribute, make it IDS, and we're gonna transfer CD and CDR. So now it's all good. We have a triangular mesh with blended attributes. This is great. We're gonna prepare the mesh for Vellum. So we're gonna type shift this, because this is an animated mesh. As you can see, there's a little clock here, which means that it's an animated geometry. So now with the time shift, we break that time dependency, and we have a static mesh. We're gonna clean this geometry because we don't need any attributes, any groups. And I'm gonna do the tet conform. What the tet conform does is tetrahedralize the geometry. It's going to create internal tetrahedrons which have volume, and they're closed geometry pieces, and they will be the constituents of this creature's volume, and they'll be deforming and creating a realistic soft body simulation. So in order to check if the tet conform worked, you use a clip attribute, clip node, just to clip your geometry. And if you clip it, you can see that all the tetrahedrons are there. They filled up the volume of this creature, and you have smaller ones closer to the surface, and for optimization purposes you have bigger ones inside the volume. This is what's going to give us the realistic movement, deformation, the volume effects in Vellum. There's nothing fake about it, like some of the constraints that Vellum offers, like the struts constraints. It's a real volume, and every tetrahedron is simulated. There's internal collisions, there's deformation, stretching, depending on the model you use for simulating them. And yeah, that's a really accurate volumetric soft body system that Vellum can use and can read attributes from. And this is why we created the entire blinking attribute system that we're going to transfer to this tetrahedral mesh along with the groups. So now we're going to also add surface triangles. Like if you go back to the tet conform, we have to check in the checkbox called add surface triangles. So now we have surface triangles, a prim group that is called like this. And now we're also going to create a group which is called tetrahedrons and group tets, GRP tets. We're going to add all the primitives, except I don't want to add the surface triangles, so let's add it here, but put a exclamation mark before it. So it's going to put all the primitives inside except the polygons, which are 61,442, and it's going to put only the tetrahedrons in a separate group. So you see GRP tets and surface triangles. We're going to also do the group transfer from our triangular time shifted mesh. So the group transfer, it takes a while, but I'm going to disable it first so I could set some parameters. I want the transfer to be really as close as possible, so the distance threshold is going to be 002. I want to transfer only the point groups, the primitive groups and the point groups, so yeah, let's do that. And just in case, I'm going to override the group name conflict, so if there's any groups that have any issues with each other, they'll override each other. So the group transfer is it may be a little bit expensive to calculate because you're transferring from a flat 3D mesh, which only has a shell, like a external surface, to a volumetric tetrahedral mesh, which has a lot more geometry in it, like three times more primitives than the original one. So yeah, so now if you want to really check for the if the groups worked, you can blast any group from the, so you can see I blasted the body. If I blast the legs, for example, I'm just going to blast the legs in volume, so the groups are propagated properly. If I blast the tail is gone. You see that there's volume there. So this is good for testing when you blast groups from a volumetric surface, a volumetric object. And we're going to recreate, like pull the IDS wrangle back here. I'm going to connect it and let it cook. It's going to take a while. And we're going to save this geometry into a BGO.sc file. Every time we do something major like this in the node tree, we're going to save and cache this file into a BGO file, which is going to save us a lot of time in the future because it's going to be baked already with all the groups, all the colors. Also, we didn't transfer any blinking attributes yet onto the object because yeah, we don't want to bake that. We're going to transfer it live in Vellum. So I'm going to do a file cache like before. I may probably copy this path here, make it explicit, load from disk, and instead of remesh, I'm going to call it tets. Single frame, save to disk. So now you have a really nice mesh, a tetrahedral mesh with a polygon surface on top with an IDS attribute with all the point and primitive groups. And in the next lesson we'll be starting to set up our Vellum system, which is going to be reading all the attributes that we created earlier. We're going to set up, in another chapter, we're going to set up the ground with the forces. So I hope you enjoyed this one, and let's meet in the next lesson.